In this section, we're going to be talking about antiderivatives. So the definition of an antiderivative says that a function capital F is an antiderivative of little f on an interval I when capital F prime of x is equal to little f of x for all x and I. So we're looking for the function whose derivative is little f. Now, one thing that's important to note is that f is an antiderivative, it's not the antiderivative. So let's talk about why that would be. If you have three functions, f sub 1 is x squared, f sub 2 is x squared plus 1, and f sub 3 is x squared minus 5, if you took the derivative of f sub 1, you're going to get 2x. If you took the derivative of f sub 2, you would get 2x plus 0. And if you took the derivative of f sub 3, you would get 2x plus 0. So all three of these have the same derivative, which means each one of these are an antiderivative of the function 2x. So you can have more than one antiderivative. Now notice the only difference between these three functions is the constant that's added on the end. So to represent antiderivatives, we want to represent all possible antiderivatives for a function. If f is an antiderivative of little f on an interval I, then capital G is an antiderivative of little f on the interval I if and only if G is of the form g of x equals capital F of x plus c for all x in I, where c is a constant. Now c is called the constant of integration. Sounds like a very epic name. The constant of integration. And it is always represented by a capital C. So if you're entering answers in WebAssign and you put a lowercase c, you probably will get the answer wrong. It is a capital C. Now the family of functions represented by G is called the general antiderivative of lowercase f. And g of x equals capital F of x plus c is called the general solution of the differential equation g prime of x equals little f of x. So a differential equation in x and y is an equation that involves x, y, and y prime. So for example, y prime equals 3x, or y prime equals x squared minus 5, or you could have something like y prime equals y plus x. I've seen things like that as well. So we're going to get into some very basic differential equations in this section. You'll talk about a little bit more later on in the course, and if you're interested in this and you want to go further, there is an entire course in differential equations. So to solve a very simple differential equation, we have y prime equals 5. The question that we're asking ourselves is, what is a function y whose derivative is equal to 5? Well, the one that I can think of is y equals 5x, and 5x could have any constant added to it because the derivative of the constant is 0. So this would be the general solution of this differential equation. So you can kind of think of antidifferentiation as the antiderivative as the undo button for the derivative. It basically reverses that process, give or take a constant. So now we're going to talk about indefinite integration. So when you solve an equation of the form dy over dx equals f of x, like we just did, we want to use the differential form we talked about in 3.9, which is dy equals f of x times d of x. Now the process of finding all solutions to this equation is what we call indefinite integration. Or you might see it called anti-differentiation. They mean the same thing. It's denoted by the integral sign, which looks kind of like this long curvy S. The general solution is denoted as follows. You have y equals the integral of f of x with respect to x. That's how you would read that. And this right here tells you the variable that you're integrating with respect to. This is what we call the integrand. It's the thing that's being integrated. And for your answer, you get an antiderivative plus the constant of integration. So finding an antiderivative and finding the indefinite integral mean exactly the same thing. So if we let little f of x be equal to capital F of prime of x, then the integral of f prime of x dx is going to be equal to capital F of x plus c. And if the integral of little f of x dx with respect to x is equal to capital F of x plus c, then the derivative of the integral of little f of x is actually just going to give you little f of x back. So what this is saying is that integration and differentiation are basically inverses of each other. They undo each other. Now we can use this to obtain several basic integration rules from our differentiation rules, and you see those in your notes. And if you look at these here, you'll notice that each of the differentiation rules that you learned has an analog for the integration formula. So the derivative with respect to x of c is equal to 0 means the integral of 0 with respect to x is equal to a constant c. The derivative of k times x is k, but the integral of k with respect to x is kx plus constant. And you can see that all of these go through as well. Now, one that I want to point out that's a little bit interesting is this one. So the derivative with respect to x of x to the n is n times x to the n minus 1, but the integral of x to the n is x to the n over n plus 1 plus c, where n is not equal to 1. So if you wanted to check this, if you took the derivative with respect to x of x to the n plus 1 over n plus 1 plus c, you would get, I'd bring out the constant first and have the derivative with respect to x of x to the n plus 1 plus the derivative with respect to x of c. So this is going to be 1 over n plus 1. I would bring down the n plus 1. I would have x to the n plus 1 minus 1, and then the derivative of c would be 0. So I would just get x to the n. So you can see that this does work, it's just reversing the process. Another thing that's interesting to point out, the derivative of sine is cosine, the derivative of cosine is negative sine, but when you take the integral of cosine, you get positive sine of x plus c, and when you take the integral of sine, you get negative cosine of x plus c. So those negative signs kind of switch places. And you can see similar patterns for all of these as well. Notice that we don't have defined the integral of tangent, secant, cotangent, and cosecant. We're not quite there yet. So using these rules, we're going to find some basic integrals, or indefinite integrals. So using this formula, this is going to be x to the 2 plus 1 divided by 2 plus 1 plus c, which is x cubed over 3 plus c. Anytime you take an indefinite integral, you have to put the plus c or you will be counted off. In this case, this would be x to the 5th plus 1 divided by 5 plus 1, all plus c, or x to the 6th over 6 plus c. And if you wanted to write this as 1/6 times x to the 6th, that's fine also. There's no reason why you couldn't do that. Now this one is kind of a power rule in hiding, so I'm going to write this as x to the 1/2 power before I start. So this will be x to the 1/2 plus 1 divided by 1/2 plus 1 plus c. Notice when I actually evaluate the integral, that's when I drop the integration symbols. So this is going to be x to the 3/2 over 3/2 plus c. And I'm going to flip and have 2/3 x to the 3/2 plus c. And that will be my final answer. So looking at some more, I could bring the 5 out and have the integral of x squared with respect to x. So this will be 5 times x to the 2 plus 1 over 2 plus 1. Now, technically, I could multiply the 5 times a constant, but 5c is just another constant, and we don't really care what the value of the constant is. We're just acknowledging that it's out there, so we just always going to stick a plus c on the outside. So this ends up giving me 5 over 3 x cubed plus c. This one I could write as the integral from the integral of x to the negative 3rd power with respect to x, which will be x to the negative 3 plus 1 divided by negative 3 plus 1 plus c. Be careful with these negative powers. They can be prone to mistakes. This is going to be x to the negative 2 over negative 2 plus c. Or if I want to bring the power down, that would be negative 1 over 2x squared plus c. And you don't have to find a common denominator or anything like that with these. You can leave it as it is. With this one, I would bring the 2 out, and I would have the integral of sine of x dx. And remember that the integral of sine is negative cosine of x, and that's all plus a constant c. So I get negative 2 cosine of x plus c. For this one, I would bring the 2/3 out and have the integral of cosine of x with respect to x. So this will be 2/3 times the integral of cosine of x is sine of x, all plus c. And for these next two, I could start by splitting this up into two integrals. So this would be the integral of x with respect to x minus the integral of 2 with respect to x. Notice each of these integrals gets the dx. That's very important. And if you do leave that notation off, I will make notes about that on your test and take off a half a point or so. So notation is very important here. Otherwise, you don't have the full meaning of what's going on. So this is understood to be x to the 1. So this will be x squared over 2. This is a constant, so this will be minus 2x. And then I just need to add my constant c out to the end. So that would be my answer here. This one right here, I might write as, just kind of doing it all in one step. I bring out the constant, have the integral of x cubed. Bring out the constant, have the integral of x squared. And then the last one would be the integral of x dx. So this will be 2x to the 4th over 4 minus 3x cubed over 3 plus x squared over 2, because remember that's x to the first power, plus c. And simplifying, I get 1/2 x to the 4th minus x cubed plus 1/2 x squared plus c. And if you just wanted to leave those as x to the 4th and x squared over 2, that's fine also.